frequently used in smart spaces, ubiquitous and proactive computing, and situation awareness applications. Robots are used in industrial automation applications, autonomous modes of exploratory operations, and others. And the spectral cameras are used in detection and recognition systems where 2D and potentially 3D spatial and spectral characteristics are very informative. But these are very different communities many times. And when you search for publications, so you don't reinvent the wheel, really publications are scattered in many domains addressing individual problems of antenna design. Many people are working on, can I really adaptively change the antenna of my point sensor so the transmission and receptions have a much better efficiency? Sensing, tiny operating system, communication protocol, synchronization schemes, wireless programming, quality of service, security, reliability. You can find a journal about each of these issues, I would say. And the same applies to robot control, tracking, automation of repetitive tasks, autonomous operation of these robots. And then if you go to the remote sensing community, let's say, you will find many of the camera calibration tasks, image understanding, real-time video processing, automated recognition, classification, compression, security, distributed computing. You can think of it. So you can see that it's a very broad spectrum of problems and related work. So our work really embraces a very broad set of individual problems and proposes and leverages from data integration across disparate sensing systems over time, space, and variable to improve system performance, and eventually reveals advantages and limitations of novel technologies. And then finally, the discriminator is that we deal with real-time monitoring applications. In comparison with past work, most of the past successful applications are not real-time. For example, the environmental and wildlife applications. There are applications in Maine, they use the sensors for monitoring some species like birds. Let's say in California, they use it for monitoring temperature and moisture of trees at different height. But these are very static applications. For some applications, the sensors even failed. For example, when you measure earthquake, clearly the sensor is not capable of being idle for, let's say, 20 or, let's say 2 years. And then suddenly there is an earthquake, and in that fraction of a second, you want to have sampling frequency, once in hundreds of a second. That sensor is not capable of doing that. So for some applications, these sensors are not even appropriate. So let me show you the first component when we deploy point sensors and using robot control. Here is a quick introduction to these sensors. They are called micro electro-mechanical systems, or they are based on this technology. We call them smart because they have some computing and communication capability. And there is a sensor board that has some sensing capability. And we run an operating system called TinyOS on these, and it was all developed by Berkeley. The hardware consists of the motherboard that has 4 megahertz Atmel processor, and it has a radio board so it can communicate. And then the plug-in sensor boards have different functionality. The one that we use have light and temperature right now, but we have others that have microphones and buzzers. They have GPS and so forth. The challenge is that there is always a battery attached to these sensors, so you have to worry about energy and and the efficiency of your processing. And then the interface board is attached to your PC, so you can program these little sensors. And also when the wireless sensors are communicating with your laptop, they go through the interface board. And here is a demo of how we deploy the sensors, very simple one. More or less, we load the platform of the robot with the sensors, and then we just remotely control the robot to move it to the desired location, and then the robotic arm is going to deploy the sensor.
This is autonomous, or it's autonomous?
We control the robot to deploy it. So the robot knows exactly the location of the sensors, and we just say, okay, move to this location and deploy. Now, if we pre-program and we say, okay, now you constructed a brand new building, and I want to deploy sensors in each room at this location, then it could be autonomous. Okay, so you can also see that as I was deploying these sensors, we had to solder the antenna to each sensor because it didn't come with it. And then we did many experiments that really explored what's the dependency of the orientation of the antenna and the shape and so forth. And again, these are electromagnetics issues. But our prime focus was to develop multiple interfaces. And here I'm showing our client-server architecture of that robot control system, where we have the keystrokes, clicks, and mouse, which are processed by one PC, which is really one interface to control the robot. Then we have the speech. More or less, I have a wireless microphone. I say, move ahead, and then the robot is going to execute that. And then we have the gesture recognition. The gesture-based robot control is probably the most interesting, and it originated from Navy. Navy had the following problem. In these days, Navy aircraft carrier decks have UAVs, unmanned air vehicles. And when you go to the airport and you see people who are called yellow jackets or flight directors, and they show move ahead and pivot left and so forth, the question is, can you build a system where you don't change anything in the current procedure, but the UAVs can be controlled the same way as these aircraft that have pilots in cockpits? The challenge is that in these kinds of environments, you have limited line of sight. There is a lot of interference, electromagnetic interference, acoustic noise, so you cannot use speech. And there are many emitters. And these people who are working on Navy aircraft decks are usually there 14 to 16 hours, so fatigue is a big issue. And they are exposed to temperatures between -10 and 140 Fahrenheit. So really, the technology that you build has to be very robust. So what we decided to do is a simple demo in our lab where we mounted some sensors on a human, and then collected data, did the recognition of the gestures, and then convert the gesture command into the instruction set of the robot, and the robot was performing the command. So the motivation and challenge is, one more time, the motivation is to allow the UAVs to mix seamlessly with the existing traffic on an aircraft carrier's deck. And the challenge is what types of sensors you should choose, whether active or passive. How do you attach sensors if you choose active? How do you acquire the data, and what's the repeatability? If I'm very, very tired, my move ahead is going to look very different than if I'm fresh. What if I'm female as opposed to male? Do I have different gestures? Clearly, there are some automatic classification issues. How do you classify? What's the reliability of that? Everything has to be real time. That's another challenge. And then eventually you have to translate the hand gesture sequence into a sequence of autonomous vehicle commands and then execute and then get some feedback. So those are also challenges when it comes to designing such a system. In terms of related work, clearly other approaches have been proposed in the past. There are vision-based systems using passive sensors. If you don't want to change anything in the Navy scenario, you just put some cameras there, and then you compute stereo, and there is either with single or multiple cameras. You acquire the video stream, and then you map the gestures into temporal signatures, and then you try to do the interpretation of that. The challenges are that in a harsh environment, the flight director, there is a different orientation of the flight director. The outdoor illumination is changing all the time, and there are possible occlusions. So the vision approach is not going to work too well. We looked at the devices with active sensors. There are devices like gloves with bend sensors or miniaturized accelerometers. And again, the constraints are that it cannot be very heavy because these people are there for 14 hours, and it has to be rugged and so forth. So eventually, we decided to go with small sensors that report Euler angles, which is yaw, pitch, and roll. And then there is a mapping, unique mapping between Euler angles and gesture motions. And it was satisfying all the application requirements. And then we published a paper that more or less analyzes what's the repeatability. So the signs really denote that we can discriminate gestures that are similar from those that are dissimilar. And then eventually the classification can work real time with